The Cassini probe has been orbiting Saturn for almost 13 years, and in that time it sent back some of the most incredible pictures and data we've ever seen. It's found underground oceans on Enceladus, methane lakes on Titan, mysterious hexagons at Saturn's poles, and so much more. Its mission ends in September when it will dive down into Saturn's clouds in a blaze of glory. But Cassini still has a lot to do in the meantime. It just finished a risky dive between Saturn and its rings, something no probe has ever done before. And it'll repeat that trick 21 more times before September. Sending Cassini through the rings will let scientists map Saturn's gravity and magnetic fields like never before, because nothing else has ever gotten this close. It was just too dangerous. The rings are made of rocks and ice moving dozens of kilometers a second, so they aren't the safest place for a spacecraft with lots of sensitive electronics. Cassini did fly through the 30,000 kilometer gap between the inner and outer rings when it first got to Saturn in 2004, but we only sent it through that big gap because we already knew it was pretty empty. Now that the mission is finally winding down though, there's not much left to lose, so it's time to send Cassini on some way more dangerous dives. The plan is to thread the needle between Saturn and its innermost ring 22 times. That gap is 10 times smaller than the gap it went through back in 2004. Cassini finished its first dive last week, but there were a few tense hours back here on Earth when we weren't sure if it had made it through. The probe used its dish-shaped antenna as a shield, just in case anything was in its path, but that also meant that it couldn't let us know if it survived until around 20 hours after it passed through the rings. Cassini made it though, and collected data the whole trip. Since we've never sent anything through that gap before, hopefully we'll learn some totally new things about Saturn and its rings. A lot of the data will take a while to process, but Cassini already sent back a few of those incredible photos that we've all gotten used to for the last 13 years, like this close-up of a storm on Saturn. Pictures like that will keep flooding in over the next months, telling us more about how Saturn's atmosphere moves and evolves. In the process, we're getting perspectives on Saturn and on the entire solar system that no one has ever seen before, which is pretty cool, and bonus, gorgeous. Speaking of new perspectives on the solar system, last week a team of researchers published a paper in the journal Nature claiming that the sun's surface might not be quite as complicated as astronomers thought. The sun has two main kinds of eruptions where particles shoot out from its surface: coronal mass ejections, or CMEs, and coronal jets. CMEs are the big ones that we need to watch out for. Each one launches billions of tons of plasma at millions of kilometers an hour, and they can endanger astronauts and interrupt communications around the world if they hit Earth. Coronal jets also fire out plasma, but they're way smaller and have much less energy. Astronomers have known for a while that both kinds of eruptions involve the sun's magnetic fields twisting and crashing into each other until plasma breaks free and flies off into space. But for years, they thought that that's where the similarities ended. It didn't seem like the same kind of twisting and splicing could make both giant explosive CMEs and those much smaller jets. As astronomers studied more eruptions, though, they discovered that they're actually really similar, so similar that there's probably one main process causing both CMEs and coronal jets, just on different scales. So this group of researchers used simulations to try and figure out what kind of twisting in the sun's magnetic fields could cause both types of eruptions. They decided to try simulating mini CMEs, way smaller than the ones we see on the sun. The fields in regular CMEs stretch over big sections of the sun and have huge loops of plasma that eventually explode out when the magnetic fields get twisted together and rearranged. So the team tried shrinking down the fields to see if the process that causes CMEs would produce something like a jet on a smaller scale. And it did! They found that even with the same sorts of things happening to the magnetic fields as in big CMEs, the resulting eruption looked pretty different on a smaller scale. As the magnetic fields twisted, the plasma got pushed together instead of spreading apart. And when it finally broke free as the fields rearranged, it all rushed out along a single line, just like what we see in coronal jets. If this is really what's happening on the sun, that means that the only difference between those gigantic CMEs and those smaller jets is the strength of the magnetic fields involved. Big fields tend to spread out and make CMEs, while small fields clump together to form jets. We're still not sure if this is actually what happens, since these are just simulations, but if it is, then we now have one unified theory to explain all kinds of eruptions, and that makes it a lot easier to study and compare them. Either way, we're one step closer to understanding the giant and sometimes dangerous explosions that burst out of our sun, and hopefully someday we'll be able to use that understanding to make better predictions about when they will happen, and give ourselves a few precious extra moments if a massive CME is about to head right for us. Thank you to our Patreon patrons for helping make this show possible. If you want to help us keep making episodes like this, you can go to Patreon patreon.com/SciShow. And if you want to watch more episodes like this, there's probably some in the sidebar. It's actually on that side. And if you want to subscribe and watch a new one twice a week, that would also be great at youtube.com/SciShowSpace, or just there's a button under the video.